California's geologic history.
California's geological history began around 500 million years ago. This was before the supercontinent historians call Pangaea even formed. Pangaea came together around 335 million years ago. The land masses covering the Earth's crust allowed it to move and come together. These land masses would become continents. Continents are made up of continental plates, and the ocean floor is made up of oceanic plates. Both of these types of plates are called tectonic plates, and they float on the mantle, a layer of magma surrounding the Earth's core. Faults, or cracks in the Earth's crust, separate different plates from one another and allow them to move and interact with each other. One of these types of interactions between plates is called subduction. Subduction is when two plates are pushed together, and due to the weight difference between the plates, one plate subducts or goes under the other. This is called a convergent fault, or a fault where two plates come together. In California, this was occurring between a denser oceanic plate, the Farallon Plate, and a lighter continental plate, the North American Plate. Around 350 million years ago, this subduction began to create the Sierras. A volcanic island on the Farallon Plate was pushed into the North American Plate. This formed a mountain, which over time was eroded as the plate continued subducting. This process of mountain building and erosion is called an orogeny, and it forms a terrain, or a part of a plate sutured onto another plate. This first terrain, created 350 million years ago, is called the shoe-fly complex. The Sierras are mainly made up of three of these terrains: the shoe-fly complex, as previously mentioned, the Calaveras complex, which formed 200 million years ago, and the Western Jurassic Belt, which formed 170 million years ago. Driving through the Sierras on our 10-day California geology trip, we observed different rocks in different terrains. To the north of the Sierras, we saw the shoe-fly complex and observed within it basalt, greenstone, and slate. Basalt is an igneous rock, meaning that it was formed from molten rock or magma. It is an igneous extrusive rock, which means that it cooled at the Earth's surface. This is often recognizable by a lack of crystals in the rock. Basalt makes up the oceanic plates on the Earth's crust, which connects to how the Farallon Plate was being pushed to the North American Plate in the form of an island. Subduction also produces great amounts of heat and pressure on rocks. When heat and pressure are applied to rocks, they chemically change and become classified as metamorphic rocks. Greenstone is a green-tinted rock that is metamorphosed basalt. Slate is also a metamorphic rock. It is metamorphosed shale. Shale is clay. It is very fine and found deep in the ocean. This further cements the idea that the shoe-fly complex was a part of the Farallon Plate, which was pushed into the North American Plate during the antler orogeny. At the end of this terrain, at a roadside stop, we observed serpentine. Serpentine is metamorphosed greenstone and has a soapy luster. This rock lubricated the two terrains to sit and slide next to each other. Next, we saw the Calaveras complex. The rock we observed in this area was limestone in the Moaning Cavern. Limestone is a sedimentary rock, or a type of rock formed by very small pieces of debris or fossils cemented together. In limestone's case, it is formed by oceanic fossils, so the debris of coral. This is further evidence to support the geologist's theory that the Calaveras complex was formed by an oceanic crust. We did not investigate rocks in the Western Jurassic Belt, unfortunately. At the same time that the Calaveras complex was forming, the Great Valley sequence began to form under the ocean. This was 200 million years ago. We observed the Great Valley sequence at Cache Creek to look into the formation of this area. The Great Valley sequence formed through sediments falling into an underwater basin and cementing into sedimentary rocks. In this area, we observed mountains made of layers of mudstone and sandstone, two sedimentary rocks that form from sediments near the ocean's shore, and layers of shale or clay, a very fine brown rock that can be found deep in the ocean. The layers formed show us that the sediments had time to settle under the influence of gravity, typical of water-formed sediments. The shale, which is formed in low-energy deposits, or the deep sea, shows us how the area used to be submerged deep underwater. The dip, or vertical direction of the layers, is subvertical, showing that at some point in California's geological history, there was a force applied to the layers to bend them in that way. After the formation of the Western Jurassic Belt terrain, the final part that we saw of the Sierras, the fault between the Farallon Plate and the North American Plate moved out into the ocean, moving the subduction past the Great Valley sequence. This is the reason why the Great Valley sequence never subducted. The subsequent subduction pushed the Franciscan melange to the surface. The Franciscan melange meaning mix in French, is a random assortment of metamorphic, igneous, and sedimentary rocks that gathered at the bottom of the ocean. The coastal mountain range was formed through the Franciscan orogeny, which pushed the melange into the North American Plate. 80 million years ago, new geological activity happened in the Sierras. The subduction of the Farallon Plate that helped to create the terrains we observed forced the Farallon Plate under the North American Plate and into the mantle. This subduction caused a great amount of heat, which began to melt the plate beneath the North American Plate. Over time, this magma rose, either pushing debris in its way up above it or absorbing it. This pushed mountains up, which in turn eroded over time. As there was less sediment on top, the magma became lighter and more able to rise even closer to the surface. The magma cooled before it reached the surface, creating an intrusion of granite, an igneous intrusive rock. An igneous intrusive rock is an igneous rock that cooled beneath the surface, giving it more time to create crystals during cooling. Although this granite was caused by the subduction that created the terrains of the Sierras around 350 million years ago, the granite is only 80 million years old, because the amount of time it took for the subducting plate to melt and the time it took for the resulting magma to rise was very great. In this granite, the gold California is most famous for can be found. This gold collected in veins in granite similar to that granite that formed the Sierras. Water in the magma helped to separate the gold and other metals from magma. This gold moved through veins or cracks in the granite, cooling and creating the veins that would be mined in the 1850s. Over time, the gold also collected in sediments in riverbeds due to erosion. This activity that created the gold resulted in the metals that we have to thank for our state's bustling economy. 30 million years ago, the San Andreas Fault was created. As the south end of the Farallon's mid-oceanic ridge began to subduct, the North American Plate came into contact with the Pacific Plate for the first time. The mid-oceanic ridge of the Farallon Plate subducted, and it was caught beneath the American Plate. This caused the plate to no longer be able to subduct, and therefore be unable to relieve the tension on the plate due to the force that started the subduction. To relieve the tension on the plate, it broke off, beginning to move horizontally in relation to the North American Plate. This new fault had a right lateral transform boundary, meaning that the plates moved past each other horizontally. This system of transform faults, is called the San Andreas Fault System. We observed the fault at Wallace Creek. The plates slide past each other at a rate of 1.3 inches per year. This offset can be observed at Wallace Creek, which the fault moves through. The creek bed has been offset by around 420 feet. Around 10 million years ago to 5 million years ago, the Sierras began to rise faster. They had already been formed, and geologists believe that they were previously elevated, but it is more recently that they reached the heights that they are now. Interestingly enough, though, the Sierras became taller on the south end of the range. There are a few hypotheses as to why this occurred. One hypothesis is that when the mid-oceanic range of the Farallon Plate subducted on the south end of the California coast, it scraped off some of the basement rock, or base igneous rock, of the North American Plate, making the land there much lighter and more buoyant and allowing it to raise up higher, therefore raising the mountains. Another theory is that around the same time, due to the North American Plate pulling apart, also known as extension, the crust of the Earth cracked and created normal faults. A section of rock dropped around these faults and others rose. This is called a basin and range system, and one is present going from California to Nevada. This extension had many effects, including the hypothesis that due to extension, weight was moved off of the Sierras in the form of a basin dropping. this form in the Sierra and Escarpment, a granite cliff formed by a fault, which caused them to be more buoyant and raised the Sierras. The formation of the large basin and range system is also attributed to magma rising close to the surface due to thinning. Many associate this with the formation of the Lung Valley caldera, which began volcanic activity around 4 million years ago due to uplift and stretching of the crust, causing magma to push up and creating faults. Volcanism in this area is young geologically, and for this reason there have been eruptions as young as the year 1350, where the Obsidian Dome erupted, forming obsidian rock. Obsidian is an unstable rock formed from a viscous rhyolitic magma. It is so viscous because it's both high in silicon and low in water. It's rarely seen as an ancient old rock because it is so unstable. Over time, it crystallizes into rhyolite. 10 million years ago, more happened than just the Sierras rising again, though. 10 million years ago, volcanism began at the Cascade Range area. The volcano that our trip focused on was Mount Lassen. The volcanism in the Lassen area, up to the north, is caused by recent subduction, unlike the subduction geology observed in Sierras, which is ancient. Lassen itself is the southernmost volcano created by California's most recent subduction. In California, subduction ended when the San Andreas Fault was created, but in the north, where the mid-oceanic range of the Farallon Plate wasn't subduction, the subduction continued with the fragments left of the Farallon Plate. This fragment was now called the Juan de Fuca Plate. This subduction created volcanism in the area. The plate being pushed into the mantle pushed magma up into the surface. The interaction between the continental plate and the oceanic plate caused the diversity of igneous rocks seen in the area today. The rocks we saw were rhyolite, a continental rock, andesite, a mix between continental and oceanic rocks, as well as basalt, an oceanic rock. Not only that, but the area contained diverse amounts of volcanic activity. We saw cinder cone volcanoes, composite volcanoes, lava tubes, and sulfur vents, as well as much more. The final event before the present day that we learned about in California's geological history relates to how rocks move, rather than further back through history, where we studied how they have been created. Throughout history, the world has undergone ice ages. The two most recent ice ages that California has seen have been 160,000 years ago and 20,000 years ago. These ice ages caused large glaciers to appear, and these glaciers had the power to plow through stone. 3 glacial effects on rocks that we observed were moraines, glacial valleys, and glacial erratics. Glacial valleys are U-shaped valleys created when a glacier pushes rocks and whatever debris is in this way until it melts. The sides of these valleys are called moraines, made up by debris pushed by the glacier. We observed this in the Sierras, where glaciers had formed in the peaks. The moraines are made up of boulders rounded by the immense force of being used on them, as well as smaller rocks and other debris. In relation to this, another geological effect is glacial erratics, or large boulders in unusual places. As glaciers move, pushing stuff, they leave rocks and debris behind where it may not usually be. Like glaciers, it is also important to acknowledge that liquid water and its movement has had a major effect on California's geology over time. Moving water creates valleys and helps erode mountains. It causes the separation of layers and patterns in rocks, and overall has helped form California's geological landscape. Now we have reached today, passing over the majorly important geological events that define the state that we live in. We hope that through this video you've gained a greater understanding of our past and wonder with us what will come next.